Well, we're going to be talking about the outer planets now, and I just wanted to show you this spectacular video that you see here of Cassini flying by Jupiter. Look at those bands of circulation. Those are all going in different directions due to the Coriolis effect. You know, that's the effect that you see from the rotation of the planet. The great red spot there it's a gigantic storm. And another thing to point out is notice that the equatorial regions are much more active than towards the north and the south. So really a lot of cool things going on. What a great video that was put together by Cassini. Well, they also had a probe that went into the atmosphere, a Galileo spacecraft, and that probe went into the atmosphere. It lasted 61 minutes before it was destroyed at about 24 bars or 24 atmospheres of pressure. So we were able, though, to get the concentrations of the atmosphere, and of course we got helium and hydrogen and all the things you'd expect, nitrogen. But we also found out that the outer part, at least, of the atmosphere is enriched in things like methane, sulfur, argon, krypton, those kinds of things. Well, this first picture I wanted to show you is of the Jupiter Aurora, auroras. The auroras on Jupiter form in the same way that the Earth's auroras form, the Aurora Borealis and Aurora Borealis. And that's from the magnetic field. When the solar wind hits the magnetic field, the particles are carried around to the atmospheres on Earth, and they slam into the atmospheres, and they, of course, cause the spectacular light shows that you see in the higher latitudes. And the same thing's happening on Jupiter. Jupiter has a magnetic field, and when the solar wind smashes into that magnetic field, those particles are carried around and they smash into the atmosphere. The only thing is that the aurora on Jupiter is a little bit different in that you have these spots. Do you see them? There's a spot for Io there. That's where Io is intensely volcanic. So you have volcanic eruptions, and some of that material it gets carried through the magnetic field up to the northern and lower latitudes of Jupiter and smashes into the atmosphere at that one spot. And we have lesser ones coming from Europa and Ganymede, which are also moons of Jupiter. So kind of cool, and I've showed the inset down there just to show you what, the fact that the magnetic poles or the actual poles of axis are different than the poles that the auroras are showing, that is the magnetic poles. Well, how do we get this magnetism? Well, hydrogen in the interior, H2, is actually a liquid, and it behaves like a metal at those high pressures, and so you get electrons. You're familiar with this, no doubt. Metals carry electrons, and so anything that behaves like a metal, like hydrogen, would be able to carry electrons. H2 as a liquid behaves like a metal under great enough pressures, and it'll carry electrons, which will induce a magnetic field, and so that's the origin of the magnetic. Well, you need convection and you also need rotation, but you have all those. There is a gigantic storm on Jupiter called the Great Red Spot. We have found that these storms have life cycles of about 150 years. So we would expect the Great Red Spot to dissipate at some point. And you can see that it's getting smaller since 1995. The last picture there at the bottom is taken in 2014. So we're starting to probably see it run its course, so to speak. And I do want to point out that in the interior, I should say on the exterior, we do have gaseous hydrogen and helium, but we have less helium in the atmosphere of Jupiter than down in its so-called mantle of liquid hydrogen. 23% of helium in its atmosphere, but we have more down there where it says metallic hydrogen in that sort of mantle type region. 27% hydrogen down there. Why I'm telling you that is that probably in the outer atmosphere we've got, or in the atmosphere we've got it raining down on top of the metallic hydrogen below, and so that's how you increase the content of helium and also neon in the mantle. I reluctantly call it mantle because I don't want you to think it's rock, in that purple area that you see there. The core is made up of rock and ice. The pressure, get this, 40 megabars pressure and 15 to 21,000 degrees Kelvin, and still you've got ice and rock down there. It's not melted because of those intense pressures. So huge pressures down there, and then keep these things solid. Also, Saturn has rings, not many, but it does have rings. It also has 67 moons. Let's take a look. 67 moons at current count. The only ones worth mentioning, though, are the 4 you see here. Going from Jupiter, and going outward, Io, Europa, Ganymede, Callisto. Ganymede's the largest. And the cool thing is that they're all within the plane of the equator of Jupiter, which should remind you of how the planets are in the solar system. And so we think that at one time Jupiter had a disk around it, and these moons swept up the material in that disk. I mean, there's some rings still there, probably left over from that disk. The same with Saturn, as we'll see. The masses are distributed, as you see below, with Ganymede being the largest mass-wise. But all the other moons, what is that, 63 of them, have only 0.03% mass. And they're probably captured planets, probably from the Kuiper belt, but maybe from the asteroid belt. Don't know precisely. The moons around Jupiter are interesting enough to take a look at in some detail. Here are there's a volcanic eruption actually occurring on Io, if you can believe that. Look at that. So this is the only planet in our solar system we know to actively be blowing off volcanoes. We suspect there are some in Venus, like I mentioned before, but and I say the only object in our solar system. Of course, we have them on Earth, but this is the first documented case of one erupting on the surface of Io. All that yellow is due to sulfur and sulfur compounds, so it's probably melting, partially melting, and concentrating the sulfur through the partial melting process, and Io then is producing these sulfur volcanoes. Kind of cool, especially for volcanologists like me. I really get excited about this stuff. I will say that the energies to generate this kind of melting inside are probably due to the tidal pulls that Jupiter has on Io. Io's closest of all these 4 planets. It's closest, and so it's probably got the biggest tugs on it of any planet. So it's, or I should say any moon. So it's really being tugged on, generating melting from the energy. Well, I think one of the cooler moons in the solar system is Europa. This is the surface of Europa. You can tell immediately that this ice that you see here has been broken up, and probably meteorites smashing into the planet, breaking the outer ice layer up into particles, and then it refreezing again. You can even see some strike-slip offset there if you look carefully. So maybe some faulting taking place in the ice of all things. Don't find that very often. Well, the cool thing about Europa is that it's got water, and you know we always talk about habitable zones in the solar system, and so you're talking about roughly the area kind of around Earth and Venus. That area is the so-called habitable zone. That's where liquid water can exist on the surface of a planet, and so we've been looking around for planets and objects that are within that zone for life. But gosh, we got water on Europa, so where there's water, there's potential for life, and so it's kind of forced us to rethink habitable zones, if you will, and where we should be looking for life, not only in our solar system but other solar systems. We'll talk more about exoplanets and the search for exoplanets a little later on. So Europa has an ocean below it. Now the tidal energies are great enough from the pull of Jupiter to have the ice melt. The ice is only about 10 kilometers thick, only, that's quite a bit. But the ocean is very deep. It's about 100 kilometers thick ocean. I mean, that then equates to more liquid water on Europa than on Earth. So got to go look at this place at some point. And it's got a seafloor. So you got a seafloor of rock, just the way the Earth is. Big candidate lately for potentially going in and finding life. Now, one of the things that is kind of, well, not kind of, it's very interesting, is that we see a magnetic field around Europa, and we think that that magnetic field is due to Jupiter's magnetic field inducing a magnetic field and electrical current, I should say electrical currents, to flow in the water. Now, you couldn't get electrical currents if it was just plain water. You'd have to have salty water. Convection and flowing water and the magnetic field generating electron flow, not the kind where you go and you get zapped from it. I'm talking about electric flow that generates magnetic fields, and so from that magnetic field we can infer that Europa has a saltwater ocean in it, which is really cool. The densities tell us that that's probably the case too. So we could have salty water down there. It looks like a great environment. You got an ocean floor. That ocean floor could be producing hydrothermal springs, which is the place that we think that the earliest life formed on Earth. So, this is a place I think we want to put on our radar for going and visiting and looking at further. Here's just the interior of Europa. It's a differentiated planetesimal, if you will. It's got a metallic core, a rocky interior made up probably of pyroxene and olivine, with water on the outside. What more could you want? So there's talk about sending a probe and collecting samples, maybe even by 2018. We'll see if they can get their act together to do that. Ganymede is very similar. It's the largest moon. It's got saltwater ocean probably, with lots of ice around it, but unfortunately below the saltwater it's believed there's an ice layer, and then the rocky mantle, and then finally it has an iron nickel core, and that core is probably a liquid on the outside. So it has a liquid core and saltwater ocean, another potential place. I think everybody's focused on Europa right now, but Ganymede is also a potential place too, since it has a saltwater ocean. I would just like to mention Callisto in passing. It's heavily cratered, so it's probably not older than 3.8 billion years due to seeing the effects of the late heavy bombardment. This is ice, by the way. It's cool for geologists because there's some landslides inside these craters. That's kind of neat. You don't usually see that on other planets, although it's a common feature on Mars. Well, let's go out and take a look at Saturn. Saturn has auroras just like Jupiter, and they're caused the same way, so I won't repeat myself. They do not have spots like we found on Jupiter for Io and Ganymede, Europa, but it does have auroras both on the north and the south poles. And you can see this ring, Saturn's known for its ring, let's face it. Here's a picture of the rings. Spectacular, aren't they? And there's that dark area in the rings you see there. That's from a moon that's been flying around inside the rings, picking up material. So we know that these objects get bigger and sweep up material within their gravitational pull. And we see it happening within the rings of Saturn. So that's a very good example, and we'll talk more about that later on. Saturn has all the things that Jupiter has in the interior. the gaseous hydrogen and in the outer atmosphere, and there seems to be helium rain. The helium concentration in the atmosphere is 14%, but helium in the where the metallic liquid hydrogen is at a concentration of 30%. So it's raining much more helium and neon on Saturn than it was on Jupiter, which is of interest. The interior, get this, 10 megabars and 8,500 to 10,000 degrees Kelvin. So still solid, though, in the inner core. And the fact that these big gaseous planets have rocky cores is going to be very important when we talk about how these objects formed. That's significant. The gases must have collected after the rocky cores formed. Let's take a look at the moons of Saturn now. There are a total of 62 moons at last count, along with some rings on along with the rings, and there are 7 major satellites, and they all are within the rings. Those major satellites all are in a planar area that's equal to the equator of Saturn, along with the rings. I want to pay particular attention to Enceladus, point to it here, because I'm going to talk about that one a little bit later on. If you move out from this picture, you're going to find Titan. Titan's kind of a cool place. Titan is the biggest of Jupiter's moons, and it's probably a captured satellite. So, because it's outside of the equatorial plane, like the other planets, or some of the other planets. But it's worth looking at. It's from the Kuiper Belt, by the way. But look what's going on the surface. We sent Cassini there to take pictures, and it picked up these lakes. And what's crazy about this is the lakes are made of ethane and methane. So we've got liquid carbon compounds on the surface. It's the only object in our solar system besides Earth that we know liquid exists on the surface. That's very cool. There are clouds that cover most of Titan. So we had to look at not most, but the northern. This is the South Pole, the North and the South Poles. But we shot through this with radar, and we were able to pick up these lakes. And look around the edges of the lakes. You'll see little dendritic patterns, so you know that this is flowing. Now there was clouds over it, and then they moved away, and we could see that the lakes had gotten bigger. So we actually think it's raining methane and ethane on the surface of Titan. Well, how cool is that? So all this since 2004. They discovered this in 2004. So a lot of things have been happening. Well, one of my favorite little places in our solar system is Enceladus, and Enceladus is noteworthy because of these plumes that are coming out of it. And they saw these, and they said, oh my gosh, let's go back and sample those. So they went back and they flew through them and they sampled them. And this is what the mass spectrometer, this beautifully colored diagram, has produced. The mass spectrometer measures the masses of particles, and then we know what's in there. So it has hydrogen, it has methane, ammonia, but look at the carbons, huge carbon compounds, and those are not the ones, when the mass spec takes these things in, it breaks them up, and so it can only tell us, a certain size compound. But so there probably were some fairly big organic compounds that were taken before the mass spectrometer broke them up. So we got these carbon compounds mixed in with all that methane. A really interesting place. So what's going on with the water? Enceladus is fairly far away from Saturn. We'd expect it to be solid rock of ice. So how come there's water? That's the big question. It's encapsulated in ice. Let me show you this picture. It's encapsulated in ice, so why do we have water? I showed you the chemical composition. It had water in it, and then of course that's liquid water. So you can see the surface here, it's got craters on it for the older region, but the rest of it looks pretty young. And if you go down to the south where we saw those plumes coming out, you see these big fractures. I've marked them on the picture here. And then they sent Cassini back to take a picture, a thermal image of it, and look at that. They call these the tiger stripes. but they're yellowish in color because they're showing heat. It's a thermal image, so it's picking up heat coming from the interior through the fractures, which is precisely where the water is coming out. So it's hotter. The ice is probably not frozen there, so it's liquid water. And so the big question is, how can we get liquid water below the surface of this planet? And the answer is that the methane is probably acting as an antifreeze. And so, wow, you know, it'd be cool to send up a spacecraft and fly through those plumes, collect some water, and bring it back to Earth, or analyze it there. I mean, if we brought it back to Earth, we'd have to be careful that we had it pretty well sealed and nobody opens the jar in the laboratory, but without taking proper precautions. But very interesting. And we don't, you know, if you go to Europa and we try to sample that ocean, you're going to have to have something burn through the ice and go down, sample the water, bring it back up, and then analyze it there, or bring it back to Earth. But here you can just travel right through the plumes and pick it up. So it might be easier to get a sample of the water from Enceladus instead of Europa first. Just a thought. Well, let's go out to Uranus, and I'm sorry to say we don't have a lot of data from Uranus and Neptune. Just Voyager's really been out there studying them. They have a gaseous atmosphere, but a lot of ice, and in fact so much ice that I would say that we'd probably want to call Uranus and Neptune ice giants rather than gas giants. But this picture down in the bottom here shows you that it's covered in gas. What else can I tell you about it? It's got a mantle of water and ammonia and methane, mostly methane, and it's got an iron-rich core. So that's significant when we talk about formations of the solar system. Once again, it's got molecular helium in its atmosphere, but it's not liquid in the atmosphere. And all bets are that it's an ice, methane ices, water ices, ammonia ices in the interior. So it really is an ice planet. There's a magnetic pole around Uranus and Neptune, but it's not dipolar like it is in the other planets. It's complicated. I'm not even going to get into why there's a magnetic pole there on both of these planets, or not pole, but magnetic field. But it's slight and not impressive like the other planets. Uranus has 27 moons. The 13 are actually connected with the rings, and then the 5 ones on the outside here, not including Puck, those are associated with a plane of the equator. And so they go around, probably formed from a disk that was around Uranus at one time. Uranus has rings, so Puck is within the rings. The other 5 are outside, and then the other objects that have been picked up from Uranus probably come from the Kuiper belt. And then lastly, talk about Uranus here. I mean, Uranus is so similar. Got a rocky core. You can see a picture of Neptune down there. Very similar to Uranus, as I mentioned before. Molecular hydrogen out there, lots of ice everywhere. So again, we call these the icy giants rather than the gaseous giants. Let's take a look at the moons. There's really only one moon to make any mention of. There are 14 known moons at this time, but Triton is by far and away the largest. Triton's got a lot of ice on it. We see variations on the surface of Triton. We have a nitrogen and methane frost that occurs on the surface, and it comes and goes periodically. So it's a young surface. That's kind of neat. Probably a captured planet, if I didn't mention this already, from the Kuiper belt.